This session continues to explore more aspects of the food flow from farm to fork. The first two talks will cover innovations in water and land use and contracting in the supply chain. And the third talk will begin to explore consumer perception of food production claims and how that might influence food systems, potentially affect on the food production methods and regulations. So the first speaker, Christian Peters, is Associate Professor at the Friedman School of Nutrition Science and Policy, Tufts University. Dr. Peters studies the sustainability of food systems using computational modeling and also through interdisciplinary research. Dr. Peters.
All right. Thank you for the introduction, and thank you to everyone who's here this afternoon still. Let's see. Here we go. Need to get oriented here. Okay. Let's see. There we go. All right. New setup. So I want to make a few opening remarks about why land and water, because there's other resources we could talk about, and to give you a little bit of a preview of what I want to cover over the next 20 minutes. So the first thing is that land and water, as has already been mentioned, are fundamental natural resources for supporting food systems. Most of the food that most people eat around the world is terrestrial in nature, so it's coming from land and water in terrestrial systems. It's absolutely fundamental. Within the U.S., most of that land and water is often either owned or the rights to that water are owned and held in private hands. And yet, and often used for private benefit, and yet they're also essential to the public good, both in terms of the food that gets produced, but also in terms of other ecosystem services. So we've got this situation where we've got resources that are often managed by people as private individuals or businesses, and yet they have this public benefit. Now, in the context of thinking about supply chains, and we've heard a lot about alternative supply chains, I think examining feasibility is often considered a private or a business issue, although it's not only that, but it definitely, in the context of sustainability, is also a public good issue. So there's this question of how do we do it, and who pays for it, and how does it get done? So what I want to do today is give a little bit of background context on land and water and why they're important in terms of sustainability, then talk a bit about transdisciplinary science as a way that we can do this assessment of feasibility and sustainability of supply chains, and then illustrate with an example from an ongoing supply chain project in the eastern United States that's focusing on broccoli supply chains. It's not a project that I'm involved in any way. I just happened to hear about it through a close colleague, but it's a nice example for illustrating the point. Okay, so a bit of context on land use change, the development of irrigation, a little bit on efficiency, because we've heard about that quite a bit today, and on the challenges of sustainability. And we'll start with a fun diagram that's going to illustrate the changes in land use in the United States over a 140-year period. It's from a publication by Weissenen and Bliss, and it's not new, came out in 2002, but it's the only one that I've seen that does this. They went back through many, many versions of the census to create a time series that represents what they call improved farmland, but is essentially analogous to what we currently call total cropland. So it's the land that we harvest plus other stuff that could be harvested. And the maps that I'm going to show you that are going to show this progression are set up in this rainbow format where colors that are either white or near the red end of the rainbow are very low percentages of a county in farmland. Yellow and green are in the middle, and then blue and purple are towards the top. All right, so we'll go through this bit by bit. So 1860, most of the land that's in farmland is east of the Mississippi. That's the big point there. 20 years later, it crosses the Mississippi and gets really dense in parts of Illinois and eastern Iowa. And the densest agriculture, you'll see, is in this rim here across the northeastern part of the country. 1900 moves west further, and the closing of the frontier would have already happened at this point. 1920 moves a little further west still, moving through most of the Great Plains. And at this point, it stops changing all that much. It concentrates a bit in the Corn Belt states by the middle of the 20th century, which was, it peaked in about 1940. And then by 1997, you see some hollowing out in the eastern United States and a settling in the middle of the country. So relatively rapid change when you think of this in geological terms. And we've now gone from being, well, long gone from being a country where we're expanding land to working with the existing footprint of land. And something similar is true for water. So we'll get to water in a minute. I want to talk about what the impact of essentially reaching our peak of land has meant for agriculture. It's meant we've continued to grow more food, not by bringing more land into production, but by increasing the productivity of that land. And worldwide, this is a very well-known phenomenon. It's measured here, this is from a report by ERS, as total factor productivity, which just means the return to all inputs you put into agriculture, including land, but also including labor and things like fertilizer. And from 1948, where they started the index here, the march in output has almost entirely been due to increased total factor productivity. That's what we've done. And achieving that, it can sometimes seems as something that's simple to increase yields or improving returns to irrigation, but it's required an awful lot of investment, which I'll touch on later. And it is indeed a simpler question than some of the questions we're asking today. So I said I'd say a bit about irrigation and have a bit of a historical perspective on irrigation. This is one of the ways that we've achieved some of this increased output per unit area. And the lifespan of this resource, in 1890, there was very little land in the United States that was irrigated. And it essentially increased through most of the 20th century. And it seems to have, sorry about that, it seems to have leveled off here at about 55 million acres in the last 20 years or so. So again, another resource that is not expanding rapidly. And the question then quickly becomes, how do you use it more efficiently? All right. I want to decompose a little bit this idea of total factor productivity with a wonderful example that comes out of another ERS report that's on the seed industry in the United States. And it uses corn as an example. So here we have back in 1900, we've got data on crop yields, about 20 bushels per acre in 1900, which is not very much. And then out to about the late 90s here at about 200 bushels per acre. Sorry, 140 bushels per acre. And then on the other line here shows productivity, total factor productivity. And those two lines are parallel. Now, let's bring in a few more pieces of information. These little arrows here, they show different innovations and how they drove this improvement in productivity. So you've got the development of a successful light tractor, then the development of corn hybrids, and then fertilizer used on 10% of acres, and then herbicide used on 10% of acres, and then hybrid corn on 95% of acres, so it's saturated, and then fertilizer use gets saturated, and then herbicide use gets saturated, and then biotech crops come in. And if you carried this line out, it would be continuing to increase, with biotech crops being the new thing that drives productivity. And I say this to give a very concrete picture of what it is that drives this, because there's research happening in all different fields that together is producing it. And that is significant. We'll come back to this idea in a little bit. Okay. So I want to throw sustainability into the mix with a slightly different picture. It's not a stool. It's not a Venn diagram. It's a collection of paradigms. And the visual is mine, but the ideas come from this paper by Welch and Graham, who wanted to differentiate three different ideas. The first idea is the predominant paradigm for most of the 20th century, which they call the production paradigm, which means increase output and increase the efficiency with which you get that output. The sustainability paradigm, in their view or in their definition, focuses on the ecological impacts and mitigating them. And then what they argued for was a food systems paradigm that also emphasized human health and today's parlance, we would add to that all the other social and community impacts that we're concerned about. And the reason I have the figure here is that they emphasized that these are additive. When you don't give up the production paradigm and you move to sustainability, you do that and you need to continue to be, or make your system more ecologically, less ecologically impactful. And when you go to the food systems paradigm, you need to also be improving human health while maintaining lower ecological impacts and having production efficiency. So it's not an easy thing to achieve. Okay, that's enough context. I want to talk now about the innovation of transdisciplinary study of food systems as a way that we can try to understand and study feasibility and sustainability of food systems in the context not just of land and water, but of any resources. And to get us started here, I want to give a quick definition of transdisciplinary science. If you've heard about it, great. If you've heard about it and been confused about it, great. I'm going to give you the best picture I know of to tell the difference between multidisciplinary, interdisciplinary, and transdisciplinary. It comes from this paper by Kajikawa from Sustainability Science. And here we go. So each of these pictures is a little flower. In the first flower, the multidisciplinary flower, it's parallel play. Multiple fields are involved, but they're not actually integrated. With interdisciplinary endeavors, you've got action happening at these interfaces between disciplines, but it's not necessarily focused. And with transdisciplinary, the emphasis is on what they call here a sustainability science core, but really could be some sort of practical question or problem or solution that you're pursuing, and that's what provides the motivation for everybody to work together, and it organizes the work. The other thing that transdisciplinary work has, not everyone agrees with this, but most definitions I've seen do, is that it involves not just academics but non-academics. That is crucial to having a transdisciplinary project. So the ingredients, multiple disciplines, working together towards some common question or problem or solution, and involving academics and non-academics. That's transdisciplinary. So now that we've got a definition, let's look at an example. And this case study is from the Eastern Broccoli Project, which, well, I'll describe in a minute. As I mentioned before, this is not a project I've been involved in directly, but I have been involved in other supply chain research, and I thought this was the best example I could come up with. So the Eastern Broccoli Project, what's it about and who's doing it? So the who it's led by Cornell University, but involves a team of other institutions and also industry partners with the goal of trying to create a regional food network for broccoli and hoping that it would also be a model for other specialty crops. The map that you see here on the right shows their yield trial locations, and in some cases there's a pairing of an institution with each of these locations. But as you can see, it ranges from as far north as northern Maine and as far south as Immokalee, Florida, which is near the southern end of Florida, and everywhere in between. The project is funded by the Specialty Crop Research Initiative, which, if you're not familiar with this is a USDA-funded program, and it requires applicants to work with stakeholders and have a stakeholder-relevant statement. It's also, by definition, going to be interdisciplinary. So it's almost de facto requiring you to work in a transdisciplinary manner, at least to try to. And in terms of the relevance here to land and water, from the standpoint of water, if you think of where most broccoli is currently sourced, which is from the western US, this would expand into a region where you're no longer necessarily relying on the irrigated water sources that you do in the western US. And in terms of land, this has more to do with, do you have the right climates and land that's accessible in the right climates to piece this industry together? Okay, so a little bit about broccoli as a product. So as I mentioned, most broccoli is currently produced in the western US. The vast majority of it from season to season, anywhere from 89 to almost all of it, almost 98% is coming from the western US, with small amounts coming from the eastern US. Now, within the current system that's shown on in the chart on the right, you can see that it's highly seasonal. The sourcing of broccoli is going to start in the spring from the southern parts of the eastern U.S., so Florida, Georgia, South Carolina, North Carolina, Virginia. And then as the season progresses, it moves north. Broccoli is a cool season crop. It needs, it can't tolerate high temperatures, so that's why you see in the summertime, it's the northern part of this region that's supplying the broccoli. It's largely Maine, but also New York and Pennsylvania and New Jersey. And then as the seasons change, it does that flow from north to south, from south to north. Kate's given me a...
I mentioned this is fresh broccoli.
Yes, it is fresh broccoli and not frozen broccoli. Frozen broccoli is almost entirely produced outside the U.S., so this is a fresh broccoli supply chain. Thank you, Kate. So you've got this seasonal nature to the supply chain. What that means is that if you want to create a year-round supply, you need to have supply from all of those members in the region. And there's some practical challenges to doing that, but one of the first questions you should ask before you invest a lot of money is, would this make sense? And one of the exercises that this team did was to create a supply chain model of the fresh broccoli supply chain to look at how much would it cost. So you might indeed be concerned about greenhouse gas emissions and energy, but let's just look at cost first. And they looked at cost for several scenarios, including the baseline and then up to 100% increase in broccoli acreage, looking at production costs and transport costs. And the bottom line of the story is that the savings in transport costs basically make up for the small increase in production costs, and you could localize this greatly without any cost to the consumer. So it's a nice example of something that is a low-hanging fruit, relatively speaking, within this sphere. But that then begs the question, all right, well, in theory this could work, but how do we make it happen? And this is where you'll really see some of the transdisciplinary aspects of this project illustrated. Because what they want to do is they need to start by breeding suitable varieties. Most of the varieties in existence now were developed for the climates of the western U.S., not the eastern U.S. Once you've got them bred, you need to test them around the region. Then once you have varieties that work, you need to grow them out so that you have enough seeds so that it can be done commercially. You also need production recommendations for the people who are going to produce this broccoli, and you have to establish a grower base among people who already know how to grow vegetables. You'll need to establish or at least enhance the distribution system for fresh broccoli, and then work to get retail acceptance and market pickup. And to do that, they've got plant breeders, agronomists, horticultural scientists, extension people, ag economists, and the industry all involved working together to actually realize this change. And that, to me, is what really makes it a transdisciplinary endeavor. But I would be misleading you if I said this was that this was easy work to do. And this summary is not from the Broccoli Project, but about transdisciplinary research in general. It comes from a paper by Brandt et al., looking specifically at transdisciplinary projects. And they identified 5 challenges, things that I've experienced in my own work. Anecdotally, I've experienced all of these things. But this comes from their study of individual transdisciplinary projects. So the first one is that they're hard to frame. It's hard to come up with that sensible question or problem that is going to motivate everyone, and that's a sensible question to answer. Then you've got to integrate methods across disciplines, and that takes time for many reasons, mostly because we're all trained in different disciplines. The research process then takes longer. That's something that Kate mentioned earlier, and knowledge production, therefore, takes longer. It requires engaging practitioners who often have different needs and timelines than the researchers, so this is not easy to create a relationship that works for everybody. And at the end of the day, if you want to generate impact, that's not easy to do. It takes so long to do the knowledge production that the impact may be it may come long after the project is considered over or done. So it's something that I don't think you easily see over one project, but probably would see looking at many projects over long periods of time. Which brings me to my last slide, which is who's going to pay for this? The slide here shows 45 years of investment from both private and public sector in agricultural R&D funding, and it shows a story that's probably familiar to many in the room. The overall story, looking at the total funding, is that, generally speaking, over the last 45 years, it's gone up with, in fits and starts. But if you look at the bottom two lines, the red line and the blue line, you see that in the last 10 years of this time series, and maybe the last 20 years, the public sector funding has leveled off, maybe decreased. And decreased certainly in the last part of this time series. And private sector has continued to increase. The reason that's significant is that these don't really replace one another. They don't necessarily substitute one another. They fund different things largely. So having them both is essential. And the type of work that I just described has been funded by public money. And if we want to see more of this, there needs to be a way to support it. And with that, I'm out of time, so thank you.